In this question, there is an interesting substitution that we need to do, and it turns out to be more complicated than it originally appears. This question actually ends up being a integration by parts question, which is kind of interesting. So we have the integral of e to the root x dx, and we like e to the x, so we go, okay, u has to be root x. Well, if u's root x, then du by dx equals 1 over 2 root x. So 2 root x du by dx equals 1. So this equals the integral of 2 root x e to the root x du by dx, which equals 2 times the integral of u e to the u du by dx. And at this point, you might see an integration by parts. W equals u, dv equals e to the u, dw equals 1, v equals e to the u. Doing an alligator, this equals 2 times u e to the u minus the integral of e to the u du by dx, which equals 2 u e to the u minus e to the u, all plus c. And now I'm going to do a substitution back, replacing u with root x. So this equals 2 root x e to the root x minus e to the root x plus c. An interesting problem. There's a little bit more to it than it first appears. In question 7, here we have two different integration questions combined into one, and it has our partial fraction decomposition and our polynomial division, and there's all these pieces. So when looking at a problem like this, if it doesn't combine nicely to start, I like to attack these problems by breaking it up into two subproblems. So the integral of x cubed plus 2x over x squared minus 1 plus x plus 1 over x minus 1 squared dx. I like to break it up into the integral of x cubed plus 2x over x squared minus 1 dx plus the integral of x plus 1 over x minus 1 squared dx. And this will break it up into two parts, which I can solve individually. And I'm just going to change my color to purple to solve, to do an aside to solve each of them individually. So here, the partial fraction decomposition, the first thing I got to do is I got to do polynomial long division. X cubed plus 0x squared plus 2x plus 0 divided by x squared minus 1. This gives me 1x terms, x squared plus 0x minus x, when I subtract, gives me 3x plus 0. So this is plus 0. This is my quotient. This is my remainder. So this implies that the integral of, or that x cubed plus 2x over x squared minus 1 equals x plus 3x over x squared minus 1. And now here, the 3x over x squared minus 1, I can actually solve that using our logarithmic differentiation using a u sub. So for the first integral, this is good enough. So we get our first integral, we're done at this point. We could keep going and doing the split and partial fraction, but we don't have to. Our second integral, we do need to break up. We have x plus 1 over x minus 1 squared. And this equals a over x minus 1 plus b over x minus 1 squared, which implies that x plus 1 over x minus 1 squared equals ax minus a plus b over x minus 1 squared. Matching coefficients, we get a equals 1 and minus a plus b equals 1, which implies that b equals 2. This implies that x plus 1 over x minus 1 squared equals 1 over x minus 1 plus 2 over x minus 2 squared. Combining all of this, we go back to our original question, pulling this down all the way down to here. The integral, this equals the integral of x plus 3x over x squared minus 1 dx plus the integral of 1 over x minus 1 plus 2 over x minus 1 squared dx. And from here, it's using all of our rules and all of our integration rules, all our formulae, and we get x squared over 2 plus 3 over 2 ln absolute x squared minus 1 plus ln absolute x minus 1 plus or minus 2 over x minus 1 plus c. And I'll leave that for you to verify. Finally, we have a definite integral that is broken up into pieces. When we have a definite integral that's over a piecewise function, we've got to break the function up into pieces based on how the function's definition is broken up into pieces. So we start with the integral from 0 to 22 of f of x dx. And this equals the integral from 0 to 3 of f of x dx plus the integral from 3 to 5 of f of x dx plus the integral from 5 to 22 of f of x dx. And this has to do with the 3 different branches of the function over this domain. And I like to draw a little number line 3, 22, and anytime it breaks, let's say at 5, I just put a little jump. And we have another, so we have a jump at 3. So we go from 0 to 3. We have a jump at 5. We don't have a jump. We're going to go all the way to 22, and it kind of looks like this. Yes, it's open, but we're not looking beyond. So it's from here to here. We have a jump at 3 and a jump at 22. Now that I've incorporated those jumps, I want to look at what values are not included and what values are included in the domain restrictions. So here, e to the x doesn't have any domain restrictions as a function e to the x, but the piecewise function has the domain restriction that it's less than 3. So for this part of the function, I can't equal 3, so I need to take the limit as b approaches 3 from the negative of the integral 0 to 3 f of x dx plus. For 3 to 5, I am defined at 3. The domain restrictions is x is greater than 0, which it's always true, but I'm not defined at 5. So this equals the limit as b approaches 5 from the negative of the integral 3 to b f of x dx plus, and it's a similar thing from the limit as b approaches 22 from the negative, the integral from 5 to 5 to b of x cubed minus 3x squared dx. Now, or sorry, let's just write as f of x. Now that within this bound, the function doesn't change for each part, I can replace f of x with the part of the function. So this equals the limit as b approaches 3 from the negative of the integral from 0 to 3 e to the x plus the limit as b approaches, or with respect to x, of course, as b approaches 5 from the inside of 3 to b of x to the minus 1/2 plus the limit as b approaches 22 from the negative of the integral from 5 to b of x cubed minus 3x squared. This equals the limit as b approaches 3 from the negative of e to the x evaluated at x equals 0 to b, and this should be a b, plus the limit as b approaches 5 from the negative of x to the 1/2 over 1/2 evaluated at x equals 3 to b, plus the limit as b approaches 22 from the negative of x to the 4 over 4 minus x cubed evaluated at x equals 5 to b. Plugging these in, we get the limit as b approaches 3 from the negative of e to the b minus 1 plus the limit as b approaches 5 from the negative of b to the 1/2, 2b to the 1/2 minus 2 cubed root 3 to the 1/2 plus b to the 4 over 4 minus b cubed minus 5 to the 4 over 4 minus 5 cubed. And for the last one, it is the limit as b approaches 22 from the negative. And finally, because of all these functions are continuous, we can simply plug in the number. So this equals e to the 3 minus 1 plus 2, 5 times 5 plus 2 root 5 minus 2 root 3 plus 22 to the 4 over 4 minus 22 cubed minus 625 over 4 plus 125. And that's our solution.